Okay, this is going to be the third video on using the Lagrange remainder of a Taylor polynomial. Now, if you haven't done it yet, I would definitely watch the first two videos. In the first video, we showed where the definition came from. In the second video, we actually worked out a problem that involved the cosine, and we'll work a third problem in this one right here. Now again, in the first two videos, we talked about these two steps. So if you're not familiar with these steps, you might want to watch the first two videos, and it'll explain where this comes from. Now in this problem, what we're going to do is this. The last video we did using a Maclaurin polynomial to approximate the cosine of 0.3. In this video, we'll use a fourth degree Maclaurin polynomial to approximate, and this time we'll try one of the e functions, so e to the 0.6 power. Then we also want to estimate the maximum possible Lagrange error, and finally give a possible range in the final answer. So it'll be the same three steps that we did in the last video. Now to do this, we'll go back to our steps again, and steps look like this. And just like before, we'll actually spread these steps out so we can show all the work in between. So this is just that same series of steps, and I'll kind of scroll down here and you can see I just gave myself a little room in between where you can put each one of the steps in there. So we'll follow, it's almost going to be the exact same process that we did last time. So what we've got is this. We want to, first of all, you have to determine a polynomial. So change the function into a Taylor polynomial for whatever degree you want. In this case, we're looking for a fourth degree polynomial. And in this problem, f of x is actually going to be equal to e to the x. And specifically in this problem, we want e to the 0.6. So we want to get an approximate value of this. Now again, to begin with, first thing you've got to do, you've got e to the x over here, so we'll put our function. So we've got e to the x, and we need the Taylor polynomial for that. Now again, this is one of the common functions, so let's go back and take a look at the list of common functions, and you should be pretty familiar with this list. Hopefully, previously in your course, you've got the sine, the cosine, e to the x, you could have the natural log. These are some of the common functions. Now, in the last video, we did the cosine and used this one. In this video, we're going to use this. So we've got e to the x is equal to, and it's 1 plus x squared divided by 2 factorial, and so on, and it goes on to infinity. Now, if you use an infinite number of terms, that means e to the x is exactly equal to this Taylor polynomial. But what we're going to use is a fourth degree polynomial to approximate this. So we're just going to use these first 5 terms right here. And then rather than being equal to, this will change to an approximation. So let's look and see what that looks like. Now again, well, it's just x squared, x cubed, all divided by 2 factorial, 3 factorial, and 4 factorial. So just go ahead and first step is just write this down. So what I'll do, this is going to be, now again, it's approximate because I'm using a fixed number of terms. But I would have 1, and then the second one is going to be plus x. Then the next term would be plus x squared divided by 2 factorial. Then you'll have plus, and again, x cubed divided by 3 factorial. And finally, plus, and then you'll have x to the 4th divided by 4 factorial. So again, we use a fourth degree polynomial to approximate that. This is what it's going to look like. Now, some numbers that you're going to work with is this. We're interested in when x is equal to 0.6, so we'll have x is equal to 0.6. And also, it's a Maclaurin polynomial centered at 0. So in our problem, c is going to be equal to 0. So you'll need these two numbers as you work through the problem. Okay, the first step is to evaluate this. So e at raised to the 0.6 would be this. So e, and in place of x, we'll put a 0.6. And that's going to be approximately equal to, and just everywhere you've got an x here, plug in a 0.6. So that's going to be 0.6 plus, and then the next term would be 0.6 squared divided by 2 factorial plus, and then 0.6 cubed divided by 3 factorial, and finally 0.6 raised to the 4th power divided by 4 factorial. So it's going to look like that. Now, if you were to evaluate this, you will come out with this number, 1.8214. And what this is the fourth degree polynomial approximation at when x is equal to 0.6. We'll put a little line around this. So it looks like this. And again, what this is, it's not the exact answer, but it's an approximation of e to the 0.6. So there's the first approximation. Now the next question, and what the Lagrange remainder gives you, is that you've got an approximation, but you want to know how accurate is it. So within what range does it apply? So we'll go on to the next step. So the next step now, you got the first step done. We'll kind of check these steps off as we go through. So as we've done the first one, we've approximated the polynomial. Now find the maximum possible value of the remainder using the Lagrange form of the remainder. Now some things that you've got on this, I think I'll switch to this, a couple of these things are easy. N plus 1, this is fixed, this is fixed. This is the one that you're going to have to determine. So in our problem, we stopped with a fourth degree polynomial, which means up here that n was equal to 4. So the Lagrange form of the remainder relies on the next term, and what the next term would be, if n is equal to 4, this is actually going to be the 4 plus 1. What we're going to have is 5 factorial. 4 plus 1, this will be raised to the 5th power, and 4 plus 1, we're going to be looking for the 5th derivative. So we'll go ahead and write these over here and actually just plug in a little bit of what we know. You've got the absolute value, and then starting with this, we'll go across to here. N plus 1, since we had n 4, then n plus 1 is 5. This is going to be 5 factorial. Then you need x minus c. Well, x is equal to 0.6, and it's centered at 0. So this would be 0.6 minus 0 raised to the n plus 1, which would be the 5th power. Now the next thing you need in here, and I think I'll put this one in red, this is where you're going to have to spend some time working. You need the maximum value, we'll put it right here, the maximum value of the absolute value of the 5th derivative. So the 5th derivative of x. But the question now, of course, is, okay, what is that 5th derivative? So now that brings you to the next step. So we'll go down here, and the next thing we've got to do is to find the n plus 1 derivative. In other words, find the 5th derivative. So in this problem, actually, if you're working with e to the x, that's pretty easy to do. So the original function is f of x is e to the x. And as you know, the derivative of the e to the x is e to the x, so all these derivatives would give you e to the x. If you had the first derivative, it would be equal to e to the x. If you got the second derivative, and so on, we'll just work our way through these, e to the x. The third derivative would also be e to the x. The fourth derivative would be e to the x. And finally, the one that we're interested in, the 5th derivative of x is equal to e to the x. And we'll put a little box around that one because that's the one that you really want. So you're going to take this 5th derivative and you're going to plug it in back up here. So we'll do this. In place of this, and we'll just go ahead and erase this right now. So in place of the 5th derivative, you have showed that the 5th derivative in this case is equal to e to the x. So now what you want to do is you have to estimate this, and that takes care of this step. We'll go ahead and check that one off. So now you've got it in this form right here. And by the way, we'll go ahead and complete the absolute value. It should have this right here. So you know this, and the next step is to make a reasonable estimate of the maximum value of this thing. So what you're going to do is to come in here, and we'll kind of put a little set of brackets around this. You want to estimate the maximum value of the 5th derivative. As we talked about in the previous videos, a suggestion that works in almost every case is to, if you make just a quick sketch of this, you can generally get a good estimate right off that sketch. So we'll do the same thing on this one we did on that last one. I'm just going to make a quick sketch of the 5th derivative, which is e to the x. And again, just a reminder, we've got the the fifth derivative of x is e to the x, and we want to estimate the maximum value of that. And as a matter of fact, remember from the formula, you actually want the absolute value. So we're going to put the absolute values around this. So a quick sketch on this thing here. Again, I'll come over here and make a rough sketch of e to the x, and hopefully you're pretty familiar with what this should look like. It's just going to be an exponential function. So it'll look something like this, and then I'll go over here and do this. Again, just a quick estimate. And you want to estimate this thing in the range from here, from 0, and x in our case is going to be 0.6. So graphically, if you were to just sketch a graph, let's do it, we'll just do it in black here. And again, it's going to go from 0. Now, I'm going to say that 0.6 is about right here. And if I went all the way out to 1, say 1 would be about right here. So when x is equal to 0, it's going to go through 1. So this is going to be 1. And again, you should be very familiar, hopefully, with the fact that e to the x is just a curve that looks something like this, and it goes on up. So that's what it looks like. Now, we want, I think I'll put it in blue here. We want, this is, by the way, this graph is e to the x. So when x is equal to 0.6, then this distance right here would be equal to e to the 0.6 power. And that's what you'd actually like to find. The question is, what is that? If you knew this right here, you'd be able to get it exactly. But the trouble is, to find e to the 0.6 power, remember, that's what the original problem is. So without a calculator, you won't be able to get that. All you can get is an approximation of it. So what you want next is a reasonable estimate of this thing. So what could this thing be? What's the maximum that this could be? And to get it, again, I think I'll go back to, well, we'll just start with this right here. I'll move it out to 1. So what's a value of e to the x that you should be familiar with? Well, hopefully most people know this. You know that e to the first power, just the value of e, it should be something that you're familiar with, is about 2.718. And you should have that memorized. It's kind of like knowing what pi is. So if you went from here up to here, this value right here would be about 2.718. But you can actually be even rougher than that. All we want on this is just a rough estimate. So what I'm going to do, 2.718 is less than 3. So I'm actually going to do this. I'm going to say that the maximum possible value of this thing is 3. Now you can tell by looking at this, the minimum it would be, this would be the minimum it would be 1. And roughly, I'm going to estimate that the maximum, just to give me a fixed integer to work with, is 3. Again, we talked about this in the previous video, but if you're uncomfortable with that, if you wanted to use 2.718, that's fine. Just anything that's a reasonable estimate on this, and this looks like this. I'll also go back to one last thing that we talked about in the last video, and that was this. Don't worry too much about this. Whether you use 3 or 2.718, the difference between these is going to be so small that you won't even hardly be able to tell it. So this is a good place to put this little slide up again. And we did this in the last video. As you go through this and you make this estimate as the maximum value, I like to just say, relax. Remember, the entire thing is only an approximation. In this step, all you want is a quick approximation that will give you an estimate of the maximum value, and off you go. So whether you choose 2, 2.718, 3, roughly, it's going to wind up being all about the same thing. So what we're going to do here is this. We're going to say that the maximum of this value of, and we'll go back up to our thing here. So the maximum value of the absolute of e to the x, we are going to estimate to be 3. And that's just fine. That's going to give us a good estimate. Okay, so that takes care of the second step. You use the graph to make a quick estimate of just some number that would give you the maximum possible value. So now the third step is this. To estimate what that maximum possible value is, you just plug it into this formula right here. So we'll go ahead and all we're going to do really is, now that we've got this, we're going back up here. You know this, in place of this, put a 3. So we'll go down to here, and what that's going to look like would be this. This is going to be equal to, here's the absolute value. I've got a bar that goes across like this. Whoops, let's get rid of that. start here and go across to here. Now again, 4 plus 1, this was 5 factorial. I'm raising it to the 0.6 raised to the 5th power, and I've just showed all of this thing right here can be replaced with a 3. So stick that on your calculator, and you'll come up with 0.001944. And what this is the maximum possible error. So you've now got the maximum possible, that's going to be the Lagrange remainder. Now let's go to the third step, so we've got this one done. So what the third step says is this, is now that you've got the value of the polynomial and the maximum possible error, you can put these two together to get a range of the answer. I think I'll do it by just writing it down like this. I'll put that f of x, whatever the function is that I'm trying to estimate, it has to be less than or equal to the polynomial approximation, and then and add the error to it, so plus the maximum error, or it has to be greater than or equal to the polynomial approximation. So then we used a 4th degree polynomial. We'll just put n for right now. The polynomial approximation minus the maximum error. So it's got to fall somewhere in that range right there. Now in our particular problem, we did this. We have f of x, we wanted to find e to the 0.6. And the 4th degree polynomial approximation that we got was up here 1.8214. So we'll write that down. So we'll come back down here. This was 1.8214. And then over here, this one will also be 1.8214. But then it's going to be plus the error. Now the error was this right here. So it'll be plus 0.001944, and then minus 0.001944. So what that's going to give you is this. E to the 0.6 is going to be less than or equal to, add these two together, and you will get 1.823344. Then subtract, this is a 0, subtract this one from this one, and you'll get 1.819456. So at this point, you can go ahead and let's just put a box around that. This is going to be what the problem requested. So it wanted to know, find the range of your estimate of e to the 0.6 power. So we'll go over there. And you've got the thing, and basically you're done with the problem. Now one thing, just to give you an idea of what the exact answer is, if you were to put e to the 0.6 on a calculator, it would return this, 1.822119. Now, if you look at your answer, sure enough, the actual answer is between the upper limit of the possible answer and the lower limit of the possible answer. So it worked out right. So you've got an estimate, you got a Lagrange remainder, and your answer has to fall somewhere in between these ranges. Now, again, just to finish this up, let's, just like we did in the last video, let's graphically look at this and get a feel for how accurate this answer is. So what I'm going to do is stick the graph up, and the graph looks something like this. So what I've got is this. The blue graph represents e to the x. This red graph here represents the 4th degree polynomial that approximated it. And you've done this before, and the idea is you use the red graph to approximate the blue graph. Now, we're interested in 0.6, which is about right here. And I put a little light blue dot just to show you this is what the actual value, or the approximate value of this thing would look like. Now again, you can tell it's a pretty good approximation. The closer the red line comes to the blue line, the better the approximation. And they seem to merge over here, so we've got a pretty accurate answer. But just like we did in the last one, let's go ahead and zoom in and get a feel for what this thing actually looks like. So what I'm going to do is go over to about right here, and I'm going to zoom in just on this point. So if I start going in, now initially it looks like this. The graph is a very good estimation, so you can't tell the difference between the red graph and the blue graph. But as you get in closer and closer and closer, eventually that red graph should separate from the blue graph because remember, it's only an approximation. So we're getting close, and it looks like, again, a pretty good estimate. Now, as you zoom in closer and closer, finally you can begin to see the red graph separating from the blue graph. Now, we'll get in just a little bit closer, even say to about right here. So what we've got is this, and let's just kind of look at the different values that we're looking at here. Now, first of all, if I put my cursor right on this little light blue dot, if you look down here in the lower left-hand corner of this graph, you can see what the values are. So if I center my cursor right over that blue dot, I get a value of about 1.82. It says 138. Well, actually, it should be 8 or 1.8214. So what that is this value right here. So 1.8214 is the blue dot. Now, if I take my cursor and move it up to the actual function and put it right here, now if you look in the lower left-hand corner, you'll get the actual value of this thing, which would be about 1.8211, and actually it's 119. That's going to be this value right here. So the difference between these two is the actual error, but all we have is the estimated error. So the next thing let's go ahead and put the upper and lower limits and see what this thing looks like. I think I'll zoom out just a little bit here. So what I'm going to do is come in here and I'll draw a horizontal line through the upper limit, this one right here, and the lower limit, this one right here. And I'll put two black lines so you can visualize what that looks like. So let's do this. I'll hit this. So here's the upper limit, here's the lower limit. Now let's get a little closer just to visually point out what all these things are. So if this blue dot represents the 1.8214, if you start at the blue dot and you go up to the black line, that's this plus 0.001944. That's that distance. If you start at the blue dot and you go down, that's going to be minus that distance. So your answer has to fall somewhere in between these two. Now right now we'll go ahead and turn this thing off. And what you'll get will be this, is you'll get, here's your approximation is the red line. The black line gives you this, and all it says is that the actual function, e to the x, has to fall somewhere in between these two black lines. And sure enough, when you graph the function, you'll see that that's exactly what it does. So if we put the blue graph back in there, sure enough, the blue graph passes between these two right here. Again, just like in that last video, at first it looks like this is a very wide range here, and it looks like it wouldn't be that accurate an answer. But again, if you zoom back out, you'll begin to get a feel for exactly how accurate it is. So let's do that. We'll zoom back out on this thing. And as you zoom back out, you'll notice two things. The blue line will collapse back into the red line, and as you get far away, the difference between the two black lines gets to where it's even hard to see. It'll seem to be smaller and smaller and smaller, to the point that the two black lines almost seem to come together in a single answer. And all that really means is you've got a very accurate approximation. So if we get way out here, you can tell your exact answer is where or the approximate answer is where that blue dot is, and it's between these two lines. But you can tell it's so far away it looks like a single line. So one more time, we'll go in just a little bit closer just to see what it looks like. So as you zoom in, you'll begin to notice separation between those two black lines, that there actually is an interval. And all you're saying with this process is that if you get in closer and closer and closer, if you start with the red line and go up to the black line and down to the black line, that when you finally put the blue line in there, the actual answer has to fall somewhere in between those two. And you can tell it's a fairly accurate approximation. So visually, that's what this gives you. So again, you're saying that the answer has to fall between this line, and that's those two black lines. Now, one final thing, just before we get started, we'll go back to the rules again. I would suggest that if you follow these steps every time, it makes a pretty good path to guide you straight through the final answer. So that's a second example. The first one used cosine, the second one uses e to the x, and hopefully that gives you a little bit better understanding of Lagrange remainder.